Hi, everyone, and welcome to our Friday noon talk. It's a pleasure for me to introduce a team of 4 presenters who are joining us today from Italy. And we have Professor Maurizio Martellini, who is I'm going to hand over to you, Maurizio, and you will introduce your colleagues. But Maurizio is with the TheranostiCentre Srl group at ENEA Research Center in Brasimone in Italy. So yes. Maurizio, I'm going to hand over to you, and please present your colleagues, your 3 colleagues who will be speaking with you.
Okay, for the recording.
We look forward to hearing from you.
Yeah, okay, thanks, John. So it's an honor for me to present my colleagues. Dr. Lydia Falsone, she's the program manager. Without her, we are not able to do anything concerning business plan or like that. And we are working together on this adventure called is a limited company in the US terms, is SRL in Italy. The scientific team is done, but it's larger, by Professor Kangole Ung. Disappear from the screen, I don't see, but Professor is there. Professor Kangole Ung is a leading expert in compact neutron generator. He essentially designed technically the machine used for designing in engineering sense for this internal radiotherapy done by neutrons. And the second expert is an old friend of my colleagues, is one of the best experts in Italy concerning MCNP, Monte Carlo simulation, Dr. Massimo Sarotto. Dr. Massimo Sarotto belongs to ENEA, is the federal agency in Italy regarding alternative form of energy. So this is the core group. We have also an expert in radiochemistry to be used sometimes when we want to combine with neutron intraoperative radiotherapy with special target molecular, but I think you know better than me. And that this is the core group. If you allow me, I would like to give the floor to Lydia, who can just start to explain shortly the basic concept of his radiotherapy.
Okay. Yes, what I'm trying to do is to give you a sort of framework or who we are and what we do. So TheranostiCentre project called NEORT, Neutron Intraoperative Radiotherapy, is a clear example of technology transfer. So the initial idea of Professor Maurizio Martellini and other inventors needed the grounded technology of Professor Kangole Ung of Berkion technology to build a prototype of the art of the device called the neutron brush to be used in operating room. And of course, the skills, the method, the bunker, and all the suppliers of ENEA. ENEA is the Italian energy agency, as Maurizio told you. The application, of course, is in medical fields, and this involved all the steps to reach this kind of market. And from the technology itself, the basic technology, with all the tests that are involved in this project, including the usage, of course, in the final environment that are hospitals and clinics. And the application, of course, is that to the patient in modality of intraoperative surgery. I must say that if the technology is very well identified and sufficiently simple to define, the research part is and represent the main difficulties because these include the cooperation with many skills, with many professional figures, because as I said before, we are talking about intraoperative methodology with a new device using neutrons. So the final target that we have is to give to patients with solid cancer new device that can represent a valid possibility and, of course, an effective one for just defeat this disease and, of course, give higher quality of life to patients. So what we have done is to create this group, this working group of the main representative you see here today, try to take this idea, this basic idea, and take it to the market. So at the moment we have the prototype, who is now placed at ENEA Center of Research in Brasimone, who is near Bologna in the center of Italy. And we are waiting for all the certifications to start with the test there. And then, of course, we have the big steps concerning all the tests in the bunker and all the collaboration with the medical entities like hospital, research center, and hospital clinics, because as I said before, we are talking about a project identified for the medical applications. I hope I've been clear. If not, you are free to just ask any kind of detail.
Maybe, Lydia, you can show other slide of the presentation, helping.
Let's see if it's working. Okay. Today my computer is not working exactly very well. Let's try again. Let's try again. Okay.
No.
Okay, just a minute. Here it is. Okay.
Yes, we see it.
Okay.
Perfect. So Maurizio, if you'd like to introduce maybe the main core element of our project.
I mean, you know, I am very synthetic. No, I think we already presented enough. So let's go to other slide. Okay, this is the I mean just for let's say coherence. This is the international patent that filed in July 2021 regarding this machine. The language is also difficult for physics because it's a typical when you file a patent is legal language. But let's to see how this apparatus show itself. The second slide, Lydia. Okay, this is very rough, and then there are the basic element of our strategy. In the lower part, you see the very schematic figure how a compact neutron generator is working, essentially, but I think Professor Cangoleung will explain better, but basically...
I think we should just go back, yeah.
Basically is a neutron gun. I'm trying to use a simple language, and we have three kind of regime to be elaborated, if you want, by Dr. Massimo Sarotto through a accurate long Monte Carlo simulation. We have a three regime linked to the dose given by the neutron. The neutrons are 2.45 MeV neutrons, so are fast neutrons, are not thermal neutrons. I know that somebody think that this is a sort of a BNCT. It's not a BNCT, it's not a boron neutron capture therapy. Just an element that I explain also to my students. Neutrons are different with respect to electrons or X-rays because allow double strand breaks, and the distribution is isotropically, so you can you have not a special angle of direction. This is very important because especially important for the doctor, for the surgeon. The idea to have a spherical distribution is to fill, allow me to use some medical language, to fill the surgery cavity in intraoperative radiotherapy. So you have a surgery cavity, and the idea is to fill also the walls, and indeed we are constructing now a special neutron generator sealed with the gas. The gas is deuterium, is not a radioactive gas, in such a way to operate and please can go correct me, 2,500 hours, so for many days. So this is the schematic. The dimension of this machine is very compact, is 35 centimeters long and 30 dimension diameter. It's a sort of a cylinder you see on the small picture. From a physics point of view, any compact neutron generator has three components, three parts, and maybe you can explain the ion source, the accelerator part, and the target.
Okay, yes. Just give you a very brief description of the neutron generator that we developed for this particular application. I just want to say a few words. What is new for this neutron generator? Neutron generator has been used for many years. We first developed neutron generator for medical applications. Is for BNCT. Okay, and not just BNCT, any application, people want very high dose of neutrons, okay, high flux of neutrons. And we made a mistake that high yield, there's a difference between high yield and high flux. So when people came over and talked to us that, can you develop a neutron generator with 10 to the 11, 10 to the 12 neutrons per second. So at first, we thought it was just the number 10 to 11, 10 to the 12 neutrons per second. And so we can develop high yield neutrons generators, but applications, it came out that it's not very useful. For example, BNCT, we developed 10 to 11 neutrons per second, but the flux of the neutrons arriving at the, like the tumor or area is very low. So that means your treatment time will be very long, in order to get the required dose. So that is the mistake that most requirement for the neutron generator. Now, when we come to this applications, we develop a high flux neutron generator, high flux. So in order to do that, we don't need a high yield neutron generator. We just have a modest yield 10 to the no bigger than 10 to the 10 DD neutrons per second. So with that, and if you can design the target so that the neutron emission is very close to the patient's body, then you can get very high flux, okay? And so this is the background of our development. And you look at the schematic shown here. We start with an ion source, which is driven by radio frequency. And the advantage of using this RF-driven plasma source is you can get almost 100% atomic deuterium ions. Okay, and if you you know that for a deuterium, you have D plus, you have D2 plus, you have D3 plus. All these besides the atomic, you have molecular ions. But the molecular ions, they are not very useful because when they arrive at the target, which is titanium, the titanium absorbs some deuteriums on the surface. And so the deuterium ions coming, and then you will collide with those deuterium atoms sitting on the surface of the titanium target. And then you have the DD reactions. But the molecular ions, they will split into 2 particles or 3 particles. So the energy will share between these particles. And if you have an atomic D plus ion coming in, you have full energy for the reaction. So you know that the cross-section for DD neutrons production increase with the energy very fast, okay? So the advantage of this ion source is you have almost 100% atomic. So the production yield of the neutron production yield is higher, okay? Second is we use a PE. This is the high density polyethylene. And this material is excellent for voltage holding, and also machine it, and you can bond it, so you can do a lot of things, and you can get any size of the materials. And with this, we can couple with a titanium target, which the place where the neutrons will be produced. Now, the neutrons produced by this DD reaction is isotropic almost, okay? Depending on the energy. The higher the energy, then it's produce more forward neutrons. But it's still isotropic, okay, with the energy we're using, which is around 120 kilovolts. And so there is advantage for this isotropic property. The advantage is you can fill up a more large area with these neutrons, okay? And second is you can also go sideways to the neutrons, not only forward, sideways. The disadvantage is there are neutrons going back in the direction where the beam is coming from, the deuterium ion beam is coming from. And also, farther away from the target of the titanium target, the lower will be the neutron flux. It drops as 1/r squared, okay? So you have to put, in order to keep the high neutron flux, you have to place this neutron generator as close to the patient as possible to achieve this high flux of neutrons. I believe I described to you this neutron generator briefly, and the dimension is very compact, and the equipment you need is just a RF generator for producing the plasma, and then you extract and accelerate the deuterium ions from the ion source. And so you need a high voltage power supply. And these are the two main equipment you need for operating this neutron generator. The DD neutron generator is much safer than DT. okay, deuterium, tritium. And so don't worry about.
Yes, if you want, I can add some words about the flux, the flux in the patient. I mean the surgical cavity. That is.
Yes. Well,
yes.
It's very close to. It's about 10 to the 9 neutrons per square centimeter per second. Okay. So
yeah. Just a second, gentlemen. I think Massimo can, Dr. Massimo Sarotto can explain this kind of language that it's crucial for clinicians. So Dr. Massimo Sarotto done the MSc calculation and easily can explain these three regimes that are very fundamental in order to treat different kind of solid tumors. Massimo.
Yeah. Yes, I will give the floor to Maximo to explain the rest of the system, like the BSA and so on. You know.
Yes.
Okay.
No, I was just to comment the figure that you see in the right bottom part. That is a 2D map of the flux distribution inside the patient tissue. Here, as an example, I simulate the tumor in breast. As you can see in the bottom part, there is breast surrounded by skin and muscle. Okay, so the neutron flux is arriving directly on the breast without skin because it's the intraoperative radiation therapy. So,
I'm very sorry. If you have a new slide up showing this diagram, we are not able to see it right now. We're still seeing slide 4 if you're showing the new diagram.
Okay, no, I'll try again to.
Sorry, Lydia, I think it was okay. It is slide 4 that you're presenting.
Okay, but it's okay right now. You can see it.
Yes. Yes.
Okay. Good.
Thank you very much. Sorry, I just wanted to double check.
You're welcome.
okay. So the picture in the right bottom corner is a 2D flux map, or if you want, also a dose map, in the sense that it's proportional. And we see here different advantages, many advantages. The first one is that the highest dose are at surface. That is crucial in the intraoperative radiation therapy to have the maximum dose at the surface. This does not happen with the electron, as an example, or with X-rays. The second feature is that the neutrons diffuse like a foam, let me say. So we irradiate not only the center of the tumor bed where the primary mass was exported, but also the surrounding tissue in order to, let me say, kill possible metastases. And the third advantage is also that the neutron dose in depth decrease very, the contrary of slowly is fastly, decrease in few centimeters. I mean, if you go 1 centimeter in depth inside the tissue, the dose is the half than at surface. And practically in 4 centimeters, you deliver all the dose that you have. And this is very important to save the nearest organs, as an example. So differently from as an example, X-rays that penetrates everywhere, here the dose is focalized on the surface. And this is crucial.
Maybe Massimo and Lydia, since the audience is having trouble seeing what you're referring to, maybe you could zoom in on the figure at the bottom right, with the plus sign at the bottom right of your screen. You might
No, it's okay.
There you go. I think this might.
Okay, it's better now.
Yes.
Okay, perfect.
Yes. And this was showing what was I saying. So, please let's see just the map of the flux.
This
Yes.
one, Massimo?
Yes,
Okay.
you can see this one is also, let me say, a map of the dose.
Okay.
So as I was saying, the dose is concentrated in the surface of the tumor bed, diffuse also laterally in order to kill eventual metastasis, and in few centimeters it decreases a lot in order to save the nearest organs. And this is the peculiarity of our neutron of 2.45 MeV. And these neutrons have another important feature that their relative biological effectiveness, is around 16 at this energy. So it's very high. And so we have a gain of 16 times between the physical dose and, let me say, the equivalent dose used in gray equivalent. And so just tuning the time of irradiation, we can deliver different regime. As an example, if you want to reach 10, 20 gray of dose, we need just 5-10 minutes. And then proportionally, if you want to increase, we can reach, let me say, around 70 gray equivalent in less than 1 hour. That's all from my side.
Yeah, just a clinical comment. This map of dose obtained, of course, by MCNP, by Monte Carlo calculation, show some peculiarity of his kind of irradiation. And correctly, Massimo underlined that this is the typical of a fast neutron with this energy. Indeed, if you increase the energy of the neutron, not from from 2.45 to 10 or more, you can do that using other kind of design. The isotropic nature of the radiation disappear. You have a more forwarded. And this, of course, was the main, for my modest understanding, was the main defeat of the radiotherapy of the 70s. The energy was too high and the neutrons were acting like bullet. So, and secondary malignancy, as you call, were very high. The second aspect of his machine, the second aspect is that this machine has been, it was underlined by the presentation of Lydia. This is dedicated machine. So it's not a generic compact neutron generator, like the one that you find in the market, but has been designed, built, and in the second slide we showed to you the prototype in Brasimone, right, Lydia? So has been built dedicated to this task. This is very important. So it is not a neutron compact neutron generator adapted from other tasks to this medical task. Has been designed, constructed. This is the prototype that you see on at the Brasimone, at the center, the research center of Iena, in closer to Bologna, and the cylinder, the white cylinder, is the main component, is the neutron generator. This is, let's say, demonstration facility. So you have all these equipment. This is the vacuum pump to fill this company Neutron Generator with in the so are polymethyl metal cry. It's a resin essentially, and we need to in the second phase, in the phase, we need to invent or to adapt the machine used for these applicators for the Mobetron or for the Electa accelerator in this case.
Okay, thank you. I see that Felix has his hand up.
Yes, I have a couple of questions. So I'll start with the first one. Correct me if I'm wrong, but you said the it's a cylinder with 18 centimeter diameter. So this generator can't go inside the tumor cavity, of course. And from the diagram, I saw that you are planning to place the generator as close as to the skin. So I'm assuming, so you are expecting the tumor to be as close as to the skin for this to work. So do you envision a change in the design so that this can be taken inside, deep into the?
Yes. Yes, we already designed it, and we will the target where the neutrons are produced will into the body, the skin, about 4 centimeters.
Yes, with a tube of about, let me say, from 6 centimeters, 5-6 centimeters or larger. So you can enter in the surgical cavity.
I see. Okay.
Yeah, we done already the design in the and the machine shop is manufacturing these things.
So Felix, just to clarify, it's for intraoperative radiotherapy where this patient is opened up for surgery. It's during surgery.
Yeah. Okay. Thank you. And the second question is about shielding. So from the diagram, I saw that you have an HDPE outer layer that will moderate fast neutrons, but then you will still have neutrons everywhere with thermal energy. So I was wondering, how are you guys planning to do the shielding of the whole generator, and how do you take care of the secondary or the scatter neutrons coming from the detector to the patient?
Yeah.
Massimo.
Yeah. Yes.
Yes. In the new design, where is the sealed neutron generator, you have, let me say, the adapter, and then you have the target with the flux, with the highest flux and the neutrons that enter in the surgical cavity. Around, so in the back side and around, we will add shielding as much as you want in order to satisfy the limits in operating room.
Yeah.
It's not a problem to shield, let me say, all around, because we have the adapter that is just inside the surgical cavity.
Oh, right, because the source will go inside. You don't have.
Yes, the source is going inside, so you have just to shield the back part, let me say.
Yeah, and just no, thanks, Felix. Thanks for your question. We done all radio protection calculation, and the weight is. If you are optimistic, is around 100 kilos, but less optimistic, to say 150 kilos. If you think that the Mobetron the weight of Mobetron is more 1,000 kilos, it's problematic. Even it's less problematic if you wanted to use a gantry system for this machine, because 150 kilo is we are working with a special company, a special on these things, and they told us that they can easily design. Just this comment, and then finally, you know, I found a question for you, because you know, I found the name due to my dyslexia, epithelial mesenchymal transition, AMT. So this is radiobiology, and I would like to cooperate with radiobiologist, clinician, to see which is the effect of on the high MT due to neutrons, because it was my previous field of research, because I think that this is crucial not only for neutron, but also for alpha particles and other things. And we should appreciate if through your university we can have some exchange about the high MT epithelial mesenchymal transition due to neutron fields.
So Norma Ybarra, who is our radiobiologist, is on the call, and in fact she put in the term we just used into the chat. So
because I heard that he was having sometimes it's difficult to remember the exact term. So I have read a little bit about this epithelial mesenchymal transition. So this is related to the tumor aggressivity. So the pancreatic cancer is very aggressive type of cancer. I think is the one that it's the one that gives a less life expectancy to the patients that have it. So I mean, I could have some exchanges with you. I have not a lot of experience precisely studying this epithelial mesenchymal transition, but I know that it's very high related with the aggressivity of the tumor, as well as with the metabolism of the cancer.
It's I should appreciate it very much. And excuse me myself if I am not using right clinical language, but
it's understandable.
You catch perfectly the point.
Yeah. So yes, it's okay. I mean, I will be interested as well to learn more about that. So your hypothesis is that this therapy is going to reduce the epithelial mesenchymal transition?
Right. Thanks a lot. Yes.
Okay, perfect. Yeah, so we can look into that. I'm happy to help.
Great. So I'm conscious that we're 10 minutes over our allotted time, and I'm very appreciative that the audience is still here. I will give an opportunity for anyone else who has a question to ask it. I understand if people have to leave, but if anyone has a question, please stick up your hand. So no other questions from the floor. Also, we can also follow up offline with additional questions as they arise.
Absolutely, John. If as probably you have to finish this seminar, if somebody has any question and would like to write to us, we are ready to answer after
Great.
Next day.
So I have your email address. If anyone would like to get it, just feel free to ask me, and I will put you in contact with Lydia and the team.
Perfect.
So on behalf of the audience and myself, I would just like to thank our four speakers for a very interesting talk about neutron intraoperative radiotherapy, something that we've all learned a lot about through this talk. And